Good afternoon. It's my pleasure to welcome you to the CERIAS Security Seminar Series, and my pleasure to welcome Dr. Tamir Tassa, who is a professor and chair of the Department of Mathematics and Computer Science.
Used to be a chair.
Former chair. His sentence has expired. He's now returned to being faculty at the Open University in Israel. He has previous appointments at Tel Aviv, where he obtained his PhD, also Ben-Gurion University and UCLA, as well as several other places that he has visited and traveled through the years. He's joining us today to talk to us about non-homogeneous anonymizations.
Thank you very much. Thank you, Chris, for inviting me, and thank you for coming. So my talk today will be about non-homogeneous anonymizations. It will cover two works I did, one with my colleague Aris Gionis from Young Research Barcelona, and a graduate student of mine, Arnon Matza, from the university, the Open University, and a recent work with Mark Last and Sasha Jmudiak from the Ben-Gurion University, which is a university in the south of Israel, Beersheba. So, the outline of the talk will contain four topics. First of all, the introduction to privacy-preserving data publishing and a survey of homogeneous anonymization. I think that these parts will be you will be more familiar with. And the other two parts are the novel parts about non-homogeneous anonymization and how to use anonymized tables for classification. So privacy-preserving data publishing. So we all know the problem. There are many organizations that collect and hold large volumes of data, and it is needed to publish this data for the purposes of data mining. And the problem is that this data contains sensitive information that cannot be released as is, and therefore, in order to preserve the privacy of the individuals whose data is contained in that database, data distortion is inevitable. Privacy-preserving data publishing targets this task. How can we publish such data so that, on one hand, privacy will be preserved, at least to some extent? I will underline this expression maybe several more times later on, while, on the other hand, minimizing data distortion in order to maintain utility of the data. And it is important to understand that once the data is published, we cannot assume anything about the algorithm or query that will be applied on the data. So this is something which distinguishes privacy-preserving data publishing from data mining, where we do know in advance what is the purpose of the data of this data, what is the usage that will be made with the data. So consider a database of patients in a hospital. Here we have a toy example where each patient contains each record contains information about the patients, and this is a suppressed database in which we removed the identifying field. Here it is the name, and we remained also only with attributes which seem to be naive, namely not harmful. Some of those attributes are public and some are private. What do I mean by that? Those that appear in black are attributes that may be extracted also from external, freely accessible databases. Here it is age, gender, and zip code, where the private or sensitive attribute is the attribute that probably cannot be found elsewhere, and this is the attribute that we wish to protect from being revealed. The public attributes are usually called quasi-identifiers because it is possible to use their values and especially their combination in order to identify a person. And then if we use those identifiers, quasi-identifiers, to link records in such a table to a different table in which the name appears or the ID appears, then we have a problem. So a study by Tanya Sweeney from about 10 years ago estimated that about 87% of the US residents may be uniquely identified by the combination of three quasi-identifiers: gender, date of birth, which includes also the year, not just the month and day, and a zip code. And she used those quasi-identifiers in order to identify the identity or the record of the governor of Massachusetts from in her medical data database of a group insurance company. She paid something like, I think, $40, bought that database, and then was able to identify that gentleman. And that, of course, raised the concern that launched that field of anonymity, not launched, but gave a push to that field of privacy-preserving data, publishing and data mining. So, homogeneous anonymization. So one of the popular approaches to deal with that problem is K-anonymization. It was proposed by Sweeney and also Samarati. And the main idea in this approach, as most of you may know, is to generalize or to suppress some of the quasi-identifiers so that each record in the table will become indistinguishable from at least K-1 other records in the database when projected on the subset of quasi-identifiers. And then if we perform this, then if an adversary will look for a record of Alice in that table, he will not be able to find her record in the table to trace her record to a group of records of size less than K. So it is important to understand that in such data distortion, the data is not fully specified, but it is correct. It is accurate. Namely, we replace, let's say, the age 27 by the range of ages 20 to 29. So it is not fully specified, but if you see range of ages 20 to 29, you can be certain that the original value was indeed in that range. Such correctness is imperative in some disciplines, especially biostatistics and biomedical research. I give here references to two papers that explain why they prefer to work with anonymized table data that was anonymized this way and not by means of perturbation, where it is not clear when you see the age 37 whether it originated from 21 or from 36 or from something else. So this is one issue that needs to be understood. So let's exemplify two anonymizations. So we have here this original table, and what we see below is a two anonymization where the ages, as you can see, have been generalized. The gender has been suppressed in two of the records. Of course, suppression is a form of generalization. The same goes for the zip code. So you can see here that that if you are looking for a record of someone who is a male of the age 32 in the zip code 92142, you cannot be certain whether this is the first or the second record, and therefore you cannot, in this example, infer whether that person has cancer or heart disease. So this is an example of two anonymization. The basic tool in achieving anonymizations like that is generalization. So what we have here, one of the usual tools in performing generalizations is using hierarchical generalization trees. Namely, we can put all the values of a given attribute as the leaves of some tree, generalization tree. And then, let's say if we are looking at the value A3, it can be replaced by the value A, which stands for any of the values below it, or we can go further to a further generalization and replace it with the value AB, which covers already the 7 leaves below it, or we can go to total suppression by replacing the value with star, which is the root of the tree. This is not the only way of performing generalization. If we have, for instance, a continuous attribute, let's say age, we can replace the age with any interval that includes it. So that cannot be described as a tree, but what I'm going to discuss here is not really affected by the ways in which we generalize. This is just an illustration of a commonly used generalization method. Regarding the measures of, okay, so this is how we generalize. Now the question is, how do we measure the quality of the output? Of course, if I will suppress all entries of all attributes in the table, I will get a table which is very, very safe. It reveals no information about anyone, so anyone can sleep at night calmly with that table, but of course, there's no usage for such a table. So the one question that needs to be addressed is how to measure the information loss, and there are many actually measures that were proposed in the literature. I will just mention a few of them. The first one is the loss metric measure that was proposed by Ingar in 2002 and by Nergis and Clifton from here in a paper from 2006. Here the penalty for each generalization is a number, each cell that was generalized is a number between 0 and 1, where 0 means you did not do any generalization, 1 means you did the full generalization, namely suppression, and it is a number that reflects the number of values in the generalized entry. So if we take an attribute A that has, let's say, n specific values, A1 till AN, and if we generalize the value A1 to the subset of values A1 to AJ, then the cost by the loss metric measure will be, in this case, j minus 1 over n minus 1. You see that if j equals 1, you get a penalty of 0. If j equals n, you get a penalty of 1. And for intermediate values, you get a corresponding cost. Another measure that is the entropy measure. Here, the penalty per entry is the entropy of the unknown original entry, given that it belongs to the published subset of values. I guess that the term entropy is known to all of you? Okay. The amount of uncertainty, if I try to guess or infer what was the original value when I see only that that the age of the person is in some range. And here we have some description of the definition, but maybe I'll skip it because it's not very essential for the remaining of the talk. I will mention now two other measures that are different in their nature from the first two measures. The first one is the classification metric. And that metric, let me just show you the example. It reflects the average accuracy of the majority rule within each block of indistinguishable records. So let's take this block of 4 records which are indistinguishable. So any anonymization will be composed of such blocks of records. And I look in each such a block on the sensitive value, which is the disease in this case. And I say the following. Here, the majority of the value that appears in the most times is cancer. So I would like to pay a cost of 1 for each record which does not have the majority value. So in this case, the records flu and stroke will pay a cost of 1, as opposed, let me go to this example, if all values in that block would be the same, cancer, 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 I will pay nothing. So what is the intention behind this measure? The intention is that it comes from the understanding that such data may be used for the sake of classification, trying to infer the correlation between age, zip code, and disease. And I prefer to have such blocks over blocks like that, where the flu and the stroke disrupt the learning process. So here I pay penalty for each record which does not fit with the majority behavior in that block. Of course, I guess that you can see the problem if I'm aiming towards such blocks, such uniform blocks. There is a problem, but I will get to it in a few slides. Another measure that is aware of the way in which the data will be used, again, this is in contrast to the first two measures which I mentioned, is the private mutual information metric from a paper from 2 years ago. And this metric, again, it uses the understanding that a plausible usage of data is to infer a classifier that will take the quasi-identifiers and will try to deduce the sensitive value that goes with them. And what this measure does, it takes the quasi-identifiers, it constructs a random variable based on their distribution in the table. It does the same also for the sensitive attribute, and then it tries to minimize the mutual information between those two random variables. It's not actually two; it's k plus one. If not k, it's t plus one if t is the number of quasi-identifiers, and one is a sensitive attribute. And the mutual information between two random variables is defined here. It's the entropy of x without knowing what is the value of y, minus the entropy of x when y is given. So it reflects the amount of information that y reveals on x. It looks asymmetrical, but it is actually symmetrical. If you replace x and y, you get the same thing. So by trying to minimize that quantity, you actually try to do a similar thing to what Ingar did in his classification error, but in a much more accurate and rigorous way. Okay, so that is about k-anonymization, what we need so far. Now let's discuss L diversity. It's something that I'm sure some of you or most of you thought about when you saw some of the examples here. So k-anonymity guarantees only a lower bound on the number of records in the published table that could be linked to a specific individual. However, it does not guarantee anything about the distribution of the sensitive value in those records. So if we go back to this example, this is a table which is for anonymous, but obviously it offers no privacy for the people behind it, because if I was able to trace Bob's record in that block, I don't care that I don't know which record belongs to him, because all records suffers from the same disease, and therefore I can infer what is the disease from which Bob suffers. So this is what L diversity comes to correct, or this is the problem that was identified in the paper from 2006. And the L diversity requires that each block of identical records, or it should be actually indistinguishable records, not identical, should have at least L well-represented sensitive values, where L is some parameter which, like K, is defined by externally. So there are several interpretations of what does it mean, L well-represented values. One of the interpretations is that if we consider the distribution of the sensitive values in each block, the entropy of that distribution will be at least log L. Another interpretation is that the maximal probability of each sensitive value in each block of records will be at most 1 over L. And there is also a third interpretation, but it doesn't really matter to right now. So this is L diversity, and this is how we correct the problem that is identified here with K anonymization, or at least improve on that aspect, which is a weak aspect of K anonymization. So finally, the problem of KL anonymization. So a generalization of a table is called KL anonymous if each group of generalized records which is indistinguishable. I'm sorry for the word identical here, which is a bit misleading, is of size at least K, and the frequency of each private value in each such block is at most 1 over L. The relative frequency within each block is at most 1 over L. And then the problem of KL anonymization is as follows. Given a database with n records and two parameters, k and n, to find the closest KL anonymization to that table. And when I say closest, I mean in terms of minimal information loss, whatever the measure of information loss is. So far, any questions? I guess so far I did not say too many surprising issues. Okay, now the problem is of k-anonymity, let alone KL anonymity, was shown to be NP-hard for k greater than or equal to 3. So the first result is by Meyerson and Williams that showed that if the alphabets here, sigma stands for the size of the alphabet of each of the quasi-identifiers. So if the quasi-identifiers are very rich, they have possible values, number of possible values, which is O of n, where n is the number of records in the table, then they showed that this problem is NP-hard by showing a reduction from k-dimensional perfect matching, which is a problem in complexity that is known to be NP-complete, to the problem of optimal k anonymization. Later on, we improved that result in the following manner. Meyerson and Williams considered only anonymizations by means of suppression, and their measure of information loss is just the number of stars that you had to use. We generalized this to a much wider class of generalizations and a wide class of measures of information loss. Later on, Agrawal et al. Were able to dramatically improve the result by showing that the problem is even NP-hard when the size of the alphabets is 3. They used reduction from edge partition into triangles. This is a problem which is known to be NP-hard, in which you have a graph and you want to split the edge set of the graph into distinct triangles. This is a hard problem. Later on, yet another improvement was provided by reducing the size of the alphabet to 2, by reduction from a different problem. And if we are already into these complexity issues, I will mention a recent result that when k equals 2, the problem is in fact in P. It can be solved polynomially, and it's based on recent results that appeared in those two papers. But this is just to complete the survey of complexity issues regarding k anonymity. So this is a hard problem. This is the bottom line. So we cannot hope to solve it in an optimal manner, and therefore we have to consider either heuristical algorithms or to consider approximation algorithms, namely algorithms that do not provide the optimal solution, but provide a solution for which one can prove that it is close enough to the optimal solution. But a survey of those results and of those algorithms is beyond the scope of this talk, so I will stop with that and go into the third topic, which is non-homogeneous anonymizations. So let's repeat the main issue. KL anonymity requires that one cannot trace a given record to sets of less than k generalized records, or to infer a private value of a record with probability which is higher than 1 over L. And it is achieved by partitioning the records of the table into groups of records, and then within each group or block or cluster, whatever you want to call it, all records in that group are being generalized in the same manner. So you will get, after applying generalization, all of those records will be transformed into the same record, at least in the quasi-identifier attributes. Now, we claim that the same goals that were stated here in the first paragraph, can be achieved also without following this methodology of partitioning and homogeneous anonymizations. And we claim that the group of legitimate anonymizations, if we break out of the framework of that was described here, is widened in a significant manner. And since it is widened, it allows achieving solutions with less information, with reduced information losses. So I will explain that. Let's take this simple example of a database. And here is an example of a two anonymization of it. What you see here is that every original record cannot be traced to a subset of generalized records of size less than 2. And furthermore, if you want to infer what is the sensitive value of a given record, you have at least 2 sensitive values that could be linked to that record. So for instance, if we are looking for a female of age 30 and in that zip code, she could be any of these 3 records, and therefore, and also you have your diversity in the sensitive values that are linked to that to those records. However, let us now consider this table. This table does not look the same because here you do not have blocks in which all records have the same, they look the same. The last block of 2 records remained the same as before, but the first block of 3 records, now each of those records look the same. And I claim that the same goals that you wanted to have by KL anonymity are achieved also by that example. I will explain that in a second. But if you consider the blue entries here, there are here 4 blue entries, you see that they are more specific than the corresponding entries in the regular anonymization. So here we have a range of ages which is smaller than that. The same goes here versus here. Here we could put the exact gender male, as where here it was suppressed, and here we could put the exact zip code, as opposed to here that we had to suppress the last 2 digits. And that was possible because we now define our framework in a less strict manner as regular anonymity, homogeneous anonymity demands. So now let's explain. I said here that the table below provides the same level of privacy as the table here, and now I have to explain what I mean by that. So the original table, let's call it T, and the published generalized table, let's call it T bar, induce a bipartite graph where an edge connects a record or a quasi-identifier tuple in T with a generalized record in T bar if they are consistent. So let's take this example. What you see on the left here is the list of quasi-identifier tuples of all records in the example that was shown 2 slides ago. Okay? This side reflects the knowledge of the adversary. I assume that the adversary knows the quasi-identifier tuples of all people in the database. This is a serious assumption regarding his strength. What you see on the right is the table that I published. In this case, you see here the regular homogeneous anonymization. These here are the 3 records which look the same in the first group, and these are the 2 records in the second group. And these records already include also the sensitive value. Now, an adversary who has this and sees also this can match each of those records with all the records with which it is consistent. So if the adversary wants to trace the record of the female of age 30 in that zip code, he will not be able to know whether this or this are her record or is her record. Now let's consider the graph that corresponds to the second anonymization which I proposed. This is how it looks. Here is, as you can see, the construction, the structure of edges here is not full or complete as it was before. here it is. You see that these three and these records induce the full graph. Each one of the records here is consistent with each one of the records here. Here, the structure is different. However, I claim that if you try to locate that person, you will not be able to to infer whether his image or generalized record is this one or this one. Same for this. You could not tell whether this or this are the required, are the true generalizations of this record. Why? Because this record is consistent with this record as well as this, which is consistent with this. By doing so, we are capable of achieving the same goal, which I did not yet fully define, but this will happen in next slides, by using or by applying less generalization. Now, I will try now to explain what is the goal that I'm trying to define. So, judging on the time, maybe I will skip this slide, which you see the title, Drafts for Non-Homogeneous Anonymizations. I will skip that, and I will go to the main definition. So since the adversary knows the exact subset of the population which is represented in the table, he knows this side of the table. So he can construct this table. He also sees that table because this is the table that was published. Therefore, he can construct the bipartite graph. Now, since the true linkage between edges from nodes in the left and nodes on the right is a perfect matching in the graph, you all remember what perfect matching is? Okay, a set of edges that connect, like marriage, perfect marriage between the records on the left and the records on the right. The adversary may concentrate only on what I call matches, namely edges that are part of some perfect matching. So if we go to this graph, here this is not a very good example because here every edge is part of some perfect matchings, but I will give later on an example in which you have edges which cannot be extended to perfect matching. Therefore, the adversary can ignore such edges since he knows they cannot be part of the true picture. He has to decide what is the true picture or the true linkage, and using this knowledge, he can eliminate edges that cannot stand for true linkages. So we require that in the bipartite graph, every tuple in T, which is the table on the left, will have at least k adjacent matches, namely at least k edges that are adjacent to it, that each one of which is a part of a perfect matching. We call such anonymizations k concealment, and we looked for KL concealments, namely to find an anonymization of the table in which every tuple in T has at least k adjacent matches, and that they are L diverse, namely no sensitive value appears in more than k over L out of those matches. So this is our goal. Now, what you see here is a picture of. Okay, let's concentrate only on this circle and on this region. Ignore, please, those other three regions because this is the slide which I skipped. This is the set of all possible k anonymizations of a given database D. This is the set of all possible k concealments of the same database D. You see that this circle is wider than this, namely, if you look for the optimal k concealment, you may find one which with lower information losses than if you restrict your search to this domain. Okay. So one of the main tasks that the anonymizer has to accomplish is to identify the set of matches. Namely, he gets a graph and he needs to identify in that graph which edges can be ignored because they cannot be extended to a perfect matching. This is a well-known problem, and there are algorithms that run in time O of nm. Here n is the number of nodes and m is the number of edges. And there is also, by the way, a randomized algorithm due to two giants of computer science, Rabin and Vazirani, which is a randomized algorithm, and it finds all matches in a graph with high probability, and its runtime is that thing, O of n to the power of 2.376. By the way, did any one of you saw this number before? This is the time complexity of matrix multiplication. This is the best time in which you can perform matrix multiplication and inversion. If you improve on that problem, you can improve also here. Now, in our bipartite graphs, it is important to understand that the anonymizer knows one perfect matching. He knows the true perfect matching. Namely, I'll now switch to this. If we have on the left the records of the original table, and on the right, let's do it by squares, the generalized records, the data owner knows that this record on the right is the generalization of this, and so forth. He knows at least one perfect matching in the graph. What we showed is that if you know one perfect matching in the graph, you can find all matches in the graph in time which is O of n plus m, linear time. So this improves dramatically with respect to the algorithms that were known before, n times m, or n to the power of 2.376. You should also notice that in our graphs, the average degree of each node is going to be O of k. So m is O of kn. And therefore, we offer here a linear time in n as opposed to quadratic, or even more than quadratic time, given the other algorithms. Okay, here I describe the algorithm, but again, due to the short time, I will skip this description. And so our basic algorithm starts with a trivial generalization, and then it starts generalizing the tuples in the table in a greedy manner until all the nodes in the corresponding bipartite graph have degree of at least k. And then in the next step, we perform further generalizations until the k concealment property is met, namely until each edge in each node has at least k matches adjacent to it. And once we do that, we are certain that our generalization complies with k concealment. And we also have to take care of the L problem, and I will not describe this aspect of the algorithm. We can also make sure that the set of matches of each node is L diverse, in the sense that no sensitive value appears in them in more than 1 over L out of them. So this is basically a greedy algorithm, with the main ingredient being the graph algorithm, which I did not describe, but you understood, I hope, what it actually does, identifying the subset of matches out of the set of edges in a given bipartite graph. Okay, once again, I will do something in a much shorter way than what I intended to do. There is a problem with the method which I described here, because let's skip that. Let's go to the picture. In homogeneous anonymization, there is no way that the adversary can distinguish between this record, this generalized record, or this one, because the graph looks completely symmetric with respect to all of those edges. Namely, if the adversary is capable of identifying his target individual in that block, he will not be able to distinguish between those three images, and each one of them will be the true image of his target individual in probability 1 over 3 in this case. However, let's consider now, let's see, where was the, oh yes, sorry, it was here. Let's consider now this non-homogeneous generalization. Here, the structure of edges is not symmetric. Here, if we look for the individual behind the record R3, then it's possible that it would be this record or this record. Why? This record is connected through an edge that is part of a perfect matching. Here is one perfect matching, and here is another. This, and this. These are two perfect matchings in which this edge participates. Now, also this edge is a match in the sense that it participates in a perfect matching. However, can you find out how many perfect matchings in the graph include this edge? Can you tell me? Actually, the answer is one, because it has this edge, and this edge are a perfect matching, but there is no other perfect matching in which this edge participates. So an adversary already has here a distinction between that possible generalized record and that one. This appears in more perfect matchings than this record, and therefore he might infer that this is the image of his target individual in probability which is not 1/3, 1/3, 1/3 in this case. So this is a problem. The answer to the problem is that in order to derive such information, the adversary would have to count the number of perfect matchings in a given graph. Now, this is a problem which is equivalent to the problem of computing a permanent of a 0-1 matrix. A permanent of a matrix is like the determinant, only without the plus-minus signs. As opposed to a determinant, which is something simple that everybody can do in polynomial time, the permanent is one of the most notorious problems in complexity. I don't think that there is a problem in complexity which is has more evidence of showing how difficult it is. It is a problem that for which the best known algorithm is exponential. It is a problem in sharp P complete. Sharp P is the class of problems of counting problems. For instance, if you are given a graph and you want to know whether it has a Hamiltonian path in it, this is a decision problem which is in NP. But if you want also to count how many Hamiltonian problems are there in it, it is even a more difficult question. It is a problem in sharp P. So sharp P is the class of counting problems. So that problem was shown to be even complete in sharp P, namely from the most difficult or one of the most difficult problems in that class. It was shown also to be a problem which is hard even in the average case. Cryptographers will not be impressed by saying that this problem is hard in the worst case, because the actual case could be not hard. This problem was shown to be hard even in the average case, and there is a long line of studies that showed the connection between the average case and the worst case complexity of the permanent. And it is even very, very hard to approximate, and so it's really a hard problem. And therefore, indeed, our non-homogeneous anonymization is not, in theory, as secure as homogeneous anonymization. If we go back to this slide, this graph contains more information than this graph. However, in order to extract the information from this graph, you will have to solve an intractable problem, and therefore this graph offers essentially the same kind of privacy or for the subjects in it as this does. This offers it in an information theoretical sense. This offers it in a computational sense. But basically, all modern cryptography replaces perfect ciphers which are impractical with ciphers in which their strength is based on computational complexity. So this looks like a good replacement for the usual anonymization, homogeneous anonymization, if I show you that it offers also better utility. So that brings us, I will skip this minimality attack. Okay, here I will not skip it. What you see here are graphs of the information loss in what you see here. The upper graph is a standard K anonymization algorithm, and one of the leading ones, and the one that offers really very, very good results. What you see in that plot is the information loss in non-homogeneous anonymization. As you can see, this is K, and this is the information loss measured by the entropy measure. As you can see, it offers significant or noticeable reduction in the information loss. Now, information loss is one measure of looking at the utility of an anonymization, but the question is whether it also translates into better performance in actual data mining tasks. So in the last 5 minutes, I will try to describe the second work, which tried to examine that thing. So we showed that non-homogeneous anonymization can be used to obtain similar privacy goals as homogeneous anonymization, but with smaller information losses. That issue was also verified by a recent work from Sigmund 2010. They devised, Wong, Mamoulis, and Chang devised a different algorithm for achieving non-homogeneous anonymization, but they too showed the same conclusion, that it can achieve smaller information losses. So those findings raise the question whether such anonymizations of training data could improve the utility of data mining models that could be learned or derived from such training data. So in a work with Mark Last and Sasha Chmudyak, we examined this question in the context of classifiers. We said, okay, let's see how good or how beneficial is that concept of non-homogeneous anonymization if we wish to build classifiers based on the anonymized tables. And to that end, we devised a new non-homogeneous anonymization. The reason why we did that is because both the algorithms of ours and of Wong et al. Were quite not simple, let's put it this way, when they try in the aspect of enforcing L diversity. I did not describe this aspect of the algorithm, and what we did, we devised a new non-homogeneous anonymization algorithm which achieves L diversity in a much simpler way, and we tested our hypothesis that non-homogeneous anonymization can yield better classifiers using that algorithm. So the new algorithm, which we called NSVDIST, it's short for non-homogeneous anonymization with sensitive value distributions, solves the problem by replacing the sensitive value in each generalized record with some distribution. So, let me show you how it works. Suppose this is an original record that we wish to generalize. So what we do, we look for the record in the database which is closest to that record. Suppose this is the closest record, in the sense that here you see that the age is quite similar, the gender is the same, and the zip code is quite similar. Once we found this record, we then unify the two records, or we generalize record R1 to be consistent also with this. So this is what happens. We replace the age range with 32 to 33. We replace the zip code with a star here, because if I go one up, you see that the two zip codes are distinct, differ only in the last digit. And if the sensitive value here was flu and here it was cancer, now I will write here a list of two sensitive values. And now I will repeat it. If I want to, I will now look for the next record which is closest to this generalized record. Suppose that this is this one. I will then further generalize this record to be consistent also with this one. So look what happened. I will here there was no change. Here the minimal age was changed to 30, and here I added the next the sensitive value, which is flu. And let's do one more step. If the next record will be this is what we get. So we do this generalization starting from each original record, and then we of course we obtain a non-homogeneous anonymization, because every record will be generalized in a different way. Now, if you think that this is a strange thing that we have here, sensitive distribution, it is not really that strange because if we look on any homogeneous anonymization, you can rewrite such homogeneous anonymization in that way. You can just simply compress all of those records into one and give here a list of diseases. So it's not really a different framework. Okay, since I have only 10 seconds left, I will take. Can I take 2 more minutes? I hope I can.
Yes.
Thank you very much. So we evaluated the algorithm on 3 benchmark datasets using 2 different classification algorithms. And what we did is we anonymized the training subset of the data using 2 algorithms. The sequential algorithm, which appears to be one of the leading algorithms of homogeneous anonymization, and our algorithm. And then after we anonymized this, we tried to extract or to learn a classifier and then test the accuracy of that classifier on the test data. And we also compared the accuracy of the resulting classifiers with the baseline classifier, which is the majority rule. Okay, I will skip. Here we describe how we pre-processed the anonymized training sets in order to subject them into a classifier algorithm. And we tested it on 3 datasets that you see here. Adult mammographic nursery from the UCI machine learning repository. Here you see how many records there were in the training set, in the test set, how many quasi-identifiers, and let's ignore the diversity because, and we used 2 classification algorithms, WJ48, which is based on C4.5, and naive Bayes. Okay, so what you see here is the accuracy of the classifiers that were derived from our non-homogeneous algorithm, the sequential homogeneous algorithm, and this is the baseline. Here you see K, the value of K. Let's forget about L. And here you see the accuracy of the classifier. This is using one classifier. This is using the naive Bayes. As you can see here, the non-homogeneous anonymization was able to produce meaningful classifiers with much higher values of K than the homogeneous one, which dropped to the baseline for much lower values of K. This is for the adult dataset. Here we show the influences of L diversity, but I will skip that. This is for the mammographic dataset. Again, you see a similar behavior that the non-homogeneous anonymizations are capable of producing more meaningful results for higher values of K. And the next example is the nursery dataset, in which there is here some point in which the 2 algorithms offer similar accuracy, but again, the non-homogeneous anonymization produces better results. So let's go for a summary. So we presented the models of anonymizations that are not based on partitioning of records and on homogeneous generalization. Non-homogeneous anonymization offers essentially the same level of anonymity as its homogeneous counterpart by replacing information theoretic indistinguishability with computational one. They are characterized by significantly smaller information losses, and those smaller information losses translate also to more accurate classifiers. And I will end here. Thank you very much.
I was just wondering why you didn't compress the diseases when there was overlap. Maybe 2 individuals had the flu. Why did you show each one?
Consistency of the data. If you had, in my example, cancer, flu, heart, if I compressed it into one flu, it would change the true distribution, and I didn't want to do that. Okay.
there's one potential issue I see with this, which is if I know one record in the data set that I can actually match out, so for example, myself,
Yes.
and I know what the sensitive value is. With L diversity, that's going to take one group where instead of KL diverse, it becomes at worst K minus L minus 1 diverse.
Okay.
But I could see in the worst case with perfect matching, or with the matching,
Yes.
that by fixing that one edge, I could conceivably, the entire rest of the data set could become known.
Yes, so we have no theoretical guarantee of how much such background knowledge reduces the number of candidates, but we did do experiments with that on the actual. This was in the first work with Aris and Anon, and we found out that the effects of such a background knowledge are limited, not always to a reduction by one, but they still maintain at least L minus 1 or L minus 3 values, or sorry, K minus 1 or K minus 2 or K minus 3 values out of the original matches. But I do agree that we cannot have here, we do not have any theoretical proof about the possible reductions of that. Yes, it's only based on experiments.
Surprised it's that. Actually, I guess I'm not surprised it's that good, but that certainly is heartening, because it makes you think maybe the next step you could come up with something which would give you such a guarantee and still give similar performance. That would be
Okay.
Any other questions, comments? Well, I'd like to thank our speakers then.
Thank you.
Wondering if the slides would be up online. I'd like to see more about the details of the algorithm.